Now it's time to connect our electrochemistry discussion in with our discussion of thermodynamics and equilibrium. More specifically, we want to use thermodynamic data to calculate E of the cell, and then similarly calculate the Gibbs free energy using E of the cell, and calculate the equilibrium constant from E of the cell. So effectively interconverting between Gibbs free energy, equilibrium constant, and voltage. We won't go too much into the derivation of the equation that relates Gibbs free energy and E. You can find the derivation in the textbook if that's something that you're interested in. That being said, this formula is how we can relate the Gibbs free energy and the voltage of the cell. N here is the number of moles of electrons, and F is Faraday's constant, which you can see here. We can then use this equation to interconvert between delta G and E of the cell. Let's do an example. I want you to calculate the standard free energy change for this reaction. A good first step is to write out the half reactions. You may be able to skip this step as time goes on, but for now, I think that is good practice. So take a moment, pause the video, try to do this on your own, and come back when you either have the answer or if you get stuck. I decided to leave the oxidation reaction written as an oxidation. Of course, when you look up the voltage, you'll be given the reduction value. And I've written both the reduction and the oxidation value for this, just to be extra clear about which one I'm talking about, since I am leaving the reaction written as an oxidation reaction. Notice here that when we balance these, we have to make the electrons balance. That's why there's a 2 in front of the gold half reaction, and a 3 in front of the magnesium half reaction. So this means that there's going to be a total transfer of 6 electrons. That's going to be important in a bit. With this information, we can calculate the voltage. As usual, you can think about this in the 2 different ways, and as usual, I've written the 2 different ways out for you. So for the way in which we leave the reduction value as the reduction value, you'll get 1.52 minus a negative 2.38. Or you can use the oxidation value, and you'd get 1.52 plus 2.38. Either way, you of course get the same voltage. Now we can do a new part and solve for delta G. We can fill in a 6 into our N. That was why I talked about that being important, right? You don't want to fill in a 3 or a 2. You have to fill in how much is actually transferred. And so it's going to be the gold. This happens twice. So you'll get 3 times 2 electrons is 6. The magnesium, this happens 3 times. And so you get 2 times 3 equals 6. And if those didn't balance, you would need to balance the reaction to see. For Faraday's constant, we can just plug in our constant that I showed you on the other slide. And then for E of the cell, we'll now have our 3.9. When we get this answer, it's going to give us the answer in joules, and I asked for it in kilojoules, and so I also just added a conversion factor to convert our joules into kilojoules. Often Gibbs free energy is really reported in kilojoules just because the amounts are quite large, and so joules would be a pretty large number. So oftentimes you'll also see Faraday's constant just written as 96.5 kilojoules per times mole. So you can fill that in that way too to save that step, whichever you prefer. Now, let's do what I'm going to call a mini derivation, since it's not a full derivation, to help us connect E and K. So this is E, our voltage, and K, our equilibrium K. We now know that G is equal to negative NFE. But we also know that delta G is equal to negative RT, natural log of K, from some of our previous chapters. Now, if delta G is equal to both of these, that means that we can set them equal to each other. Now we actually have an equation that relates E and K. It's just not a very pretty equation. So we can do a little bit of rearranging to make this look nicer, getting rid of the negative on both sides and then solving for E. This gives us RT NF natural log of K. The negatives went away, the NF were divided over. You'll often see this equation written another way. And I like showing both because I think both are useful. So R is a constant. T is often done at 298, and then Faraday's is a constant. And so if you plug all three of these values in, you can get this equation, which has basically keeps this math done for you. And you'll often see this written out, and you're welcome to use it so long as you're at 298 Kelvin. Now, I like this little picture because it shows us how we can go from delta G to E, delta G to K, K to E, or E to K. And it shows us each of the reactions that we're going to use to do that. I'm sorry, that shows us each of the equations that we're going to use to do that. And this can be a very useful triangle to help you picture this way of going in between any of the three parameters that we just talked about. So if you have any one of them, you can go to any of the other ones. Let's do another example. For the most part, this is going to be using our equation between E and K. But I'm also using this as a chance to do a bit of review on acids and bases. So take a moment, look at the problem, come back if you need a hint or have solved it. If you got stuck right away because you couldn't solve for K, here's a hint. pH being buffered at 1.6 tells us the concentration of H+. This is also a little bit of a weird problem given the heterogeneous nature of K. In this case, we are able to go ahead and use K, where we are factoring in H as 1, and as a pressure, H is a pressure, and then the lead in H+ is concentration. Doing it this way makes a couple of assumptions about how pressure is related to concentration, but it's acceptable. And if we were going to do this on an exam, I would let you know that you're allowed to do that as well. So with those hints, go ahead and try and solve it again if you got stuck and came back. Now, I think watching this one worked out pretty slowly and painfully by hand is really the best way to go because it's pretty complicated. So I'm actually not going to do this in podcast style. I'm going to go ahead and cut in my lecture capture from when I worked this out with my class for you. It's a little bit slower that way. This is why I actually re-recorded those lectures in a podcast format. But for some problems, really seeing it worked out that way is the best case. And so I'm going to leave that cut in here. A couple important things with this problem. One is just the main reason we're doing it, where it's stuck in here, where it's saying, okay, we're going to go through and calculate K and G and E all off each other. There's one other thing I want to draw a little bit of attention to, because I know that this was still messing with people a little bit on their homework too, is buffered at pH 1.6. Don't forget that tells us stuff. We know what that means. We know that that means that our H+ concentration is going to be constant and that we can calculate it, right? Because we didn't forget all the stuff that we learned on midterm 1. We remember that, oh, if something is pH 1.6, how do I get H+? 10 to the negative 1.6. And because it's buffered at 1.6, it's not going to change either. The situation is set up so that it's going to be relatively stable at pH 1.6. So whenever you see that in any problem, that's what it means. It's the problem's way of telling you, this is what H+ is. Or also you could calculate OH- if we cared. In this particular problem, we don't. But we could also calculate OH-, okay? Don't forget that. All right, so now, moving on to the idea behind this problem. Calculate the pressure of H+ in atmospheres required to maintain equilibrium. In other words, that equilibrium is going to continue to happen. If you drop below this amount, it won't happen anymore, with respect to the following reaction. I tell you the concentration of lead. Let's just write this down here so we have it. Should be a molarity. And the solution is buffered at 1.6. And so we also know that this is 10 to the negative 1.6. And we want to know this. What do you have to have in order to maintain that? Okay. So we're starting this one off a little bit higher level than we did the other ones, because I trust that you can just kind of fill into the equations on your own. What we would like here, we need something that has P in it.
P of H plus. And we only really have one equation that does that. What we have is this. We know that K that our heterogeneous K is equal to this. And if we have K, we can figure this out, because we have this and that. Okay, so we go to find K, but we can't because we don't have enough information right away. But when we look at this, we say this is a redox reaction, right? If this is a redox reaction, I can find E of the cell. I can look up this half reaction. I can look up this half, well, you don't have to look up that half reaction. You know the E of that half reaction. I can figure out E cell. Once I figure out E cell, I can figure out K. Once I figure out K, I can figure out P, right? It's working the problem kind of in reverse. It's saying, this is what I would like. I would like K. I don't have K. What else could I figure out that would let me find K? So, step 1 becomes find E. We have our two half reactions. Negative 0.13 volts. So you look that up on a table, you have it. We could look up the hydrogen one on a table, but that's actually one that you need to know. So let's remember what it is first. What is it? 0, right? That's our one that everything else is relative to. So I'll write it out too, but just make sure you know it. We go to add these up. And we look at this. Our lead is being oxidized. Our hydrogen is being reduced. And so it's going to be, depending on how you want to think of it, either 0 minus a negative 0.13 or 0 plus 0.13. Okay, that's our E cell. Now that we have that, we can go through and figure out what K is. So we use our equation that I just gave you. We can fill in all our numbers as is, or we can go ahead and solve ahead of time. I'm going to go ahead and actually solve for natural log of K first, and then fill in my numbers. Why? I just find it's easier. I make less mistakes when I do it that way. You can do however you want. So we'll fill in our voltage. What R do I use here? We're dealing with voltages and energies. We want to use the one with joules. So that's our 8.31. We can fill in Faraday's constant. This is getting a little messy, so I'm going to be a little lazy with units until the end. We fill in our temperature. If you want to use the one with the numbers already filled in, since we're at 25C, go for it. I generally tend to like to just fill in the numbers each time when I'm showing you guys so you know where they're all coming from. Now let's deal with N. How many electrons were being transferred? It's 2 in each one, right? So we didn't have to multiply it by anything. It's just balanced. So it's just 2. And we solve that whole thing. How do you undo a natural logarithm? E to the power of. And we get our k. Now we have k. That was what our aim was. We fill back into here. And solve for p. There's one thing I forgot up here, so let me fix it right here. Anyone want to, what's not here that needs to be? We'll go from scratch. I was going to skip a few steps, but I don't think I want to skip a few steps on you. Oh, I'm sorry, I put that on the wrong thing. It should be down here. It was fine as was. Okay, sorry about the confusion. The P is the P of the H2 was fine. It was this that was as is. Okay. So now we have numbers. All we need to do is solve for our H2, okay? So we need to make sure that when we rearrange everything, we fill everything in, we get our P of H2, and we're all set. I'm running out of room, so I'm going to scroll up a little bit. So we take our pressure of H2, we have our K, we multiply that up, we divide that down. We know all of those numbers, so we can fill them in. To make sure you know where they're all coming from. We have that there. This comes from the pH, and this is given. Okay. It's there? Yeah. It's a heterogeneous K, so in this case you're allowed to do it. It'll kind of come up over and over in this section too, that it's actually a heterogeneous K. But good question, because it comes up in your homework a couple of times too. So we're gonna walk back through this because this is one of those where to write it out for you guys, it looks like a lot more work than it really is if you're doing it. So let's just talk through it again real quick, okay? So what we wanted was our pressure of K, or our pressure of H2, which meant we needed K. We didn't have K, but it was a redox reaction, so we found E. We filled into our one equation, and we solved for K. Once we solved for K, we could fill that into our K equation because we only had one unknown, and we were all set. Okay? So it's really only one equation or two equations that we filled into, just K and G. We just worked it in reverse. We have a couple more minutes. I have one more thing I'm going to introduce. So we just had to work it in reverse because I trust you to be able to just kind of fill in the numbers if given. So I skipped difficulty steps.
Let's do another mini derivation. When we were back in thermodynamics, we had an equation that related standard Gibbs free energy to those at other conditions. We now can take that equation and fill in our new equation, which relates G and E. And this gives us an equation for E at non-standard states. So now that we've done this, we have filled in negative N of E for both conditions, noticing that we have standard state voltage for one and non-standard state voltage for the other. So since this was G at standard state, this is going to be E at standard state. Since this is G at non-standard state, this is going to be E at non-standard state. Well, once again, this is not a particularly pretty equation, and so we can clean it up a little bit by dividing the negative NF on both sides. Now remember, if you're going to divide it on both sides, rules of fraction say it needs to go to both terms. So when that happens, this negative NF is going to cancel out, and then this RT over NF is going to stay. When we divide this negative over, this negative becomes a positive, and this positive becomes a negative. And so that's why the change in sign happened. Similarly to when we did our previous mini derivation, you'll see that we have three constants in here. And we can fill those in. Again, they like to do this with T at 298. And then we're able to fill this in here, and we can use this little bit simpler equation as well. I think both of these equations are valuable. I like knowing what these constants are, even if it means more calculator pushing. So I would think about both of these and kind of remember that both of these exist. Let's do an example at non-standard state. Similar to our last example, I think that this one's a little bit better worked out by hand. When we have these more complicated ones, having it go a bit slower and seeing how this works if you're interacting with a class works a bit better. So I'm going to go ahead and copy my lecture capture video into this as well, so that you're able to see how that plays out in live time.
Calculate the reaction quotient, or otherwise known as Q, for the cell reaction given the measured value of the cell potential. So I'm giving you what we measure, and we're going to go back and calculate Q off it. As always, we'll do this on the documenting hammer. All right, this is also a review of cell notation, right? Because we have this in this cell diagram format where we can go through and say, okay, what's happening? By giving you this, I'm telling you a bunch of information. Is this my anode or my cathode? Why? It's first, right? This is just the definition of how we set it up. So if it's the anode, is that oxidation or reduction? Oxidation. Good. Which means that this is my cathode, or my reduction. We know that right away with what's given. Now we have E. If we want to use the equation we just talked about, let's write it down a second so we can point to things and look at it. I didn't specify a temperature, so we can assume 25 degrees. So I'm going to use this one, which already has the F and the T figured in. This. Now, in order to do this, we need some information. We have E, so that we just have right here. We can fill that in. This is what we're trying to solve for. Can we figure out N? Sure. We also then need E naught, right? So there's two more things we have to figure out when we look at this. We know that this is probably the equation we're going to need to use because it's the only thing that has E and Q in it, right? So that's how we know that's our equation to use. But there's still some things we have to figure out. So let's start. It doesn't really matter which one we start with, but let's start by figuring out E naught. Okay, so we look it up on a table, same as always. We know which one is our oxidation and which one is our reduction. So when you look at this up on a table, it's going to look like this. And this. So I'm writing this just as if you found it on the table so that we can make sure we know what we're doing with it. Our table values are always reduction potentials or oxidation potentials. Reduction. But we know one of these is oxidized, right? We know that this one is actually going to be our anode. So we make a little note of that. So when we go to figure out E naught, we need to make up for that somehow. So we can do 1.23, and then we can either do minus 0.80, minus the reduction potential, or if you're thinking about it as plus the reverse, you would do plus a negative 0.8. So either 1.23 minus 0.8 or 1.23 plus a negative 0.8. Either way, you get the same answer. It's just however you want to think about it. All right, so now we have this. We're getting there. We can fill that into here. So now the only thing left is figuring out N. We don't necessarily have to balance the whole reaction to do this. We can do it by looking at the half reactions. You might not be able to do it from looking at the cell potentials. Maybe you can. It's sort of a personal preference. Since we're going to look up these values anyways and we have it, we can just look at these and say, well, okay, when we go to balance it, it doesn't really matter which method you use. We're going to need to make sure that those electrons are the same on both sides. So we need to just come up with the lowest common multiple between 1 and 2. So how many electrons are going to have to transfer? 2. You don't have to balance the reaction to find that out. You can, but you can do it just by looking at the half reactions too and save yourself a bunch of work. Okay. Now it's effectively plug and chug. So we have our 0.40 from here. We have our E cell naught from here. Our 2 because of that. Natural log of Q, which is what we're solving for. So that's fine. Make sure you do your order of operations correctly. So subtract that over, times by a negative 2, divide by that constant. You'll raise the whole thing to the power, or e to the power of. And you get right about 10. There's a decimal point there just to add that extra so that it doesn't look like we're rounding that much, because it is really close to 10. Things to be a little bit careful of here. It didn't come up because we didn't talk about temperatures. But if we had to fill in a temperature and had to use the other form of the equation, what unit does temperature have to be in? Kelvin. It's almost always reported in Celsius. Just make sure you switch it to Kelvin. If you're getting answers that don't make any sense, that's probably because you didn't switch that. Generally, these are going to be small changes. You're not generally going to have something that makes it extremely different. It's kind of because of that logarithm there. So keep that in mind. If you get something that just skyrockets high or low, probably there's something a little bit wrong. Go back, recalculate it.
In review, we now have related voltages to our thermodynamics parameter Gibbs free energy and our equilibrium constant K. We've done this at both standard conditions and non-standard state conditions. And we now have a triangle that lets us relate between these three parameters based on these equations.